today's class we're going to be using the losses in bends apparatus to determine the system resistance curve. If you recall from the practical that we did with the losses in bends, the tapping points across each fitting, whether it be the short elbow or the short bend and the other fittings, managed to determine a difference in piezometer level from which we can look at determine the losses at each tapping point. So we're going to use this apparatus again, but this time we're not interested so much in the individual losses across each of these fittings, contractions, expansions, short and large elbow and gate valve, but measuring the total system losses. In other words, the system losses from the entrance to the exit. So if we follow the tapping points, we'll see that the outlet, which is point O, is found by this tapping point, and which comes to the exit of the system, and the inlet, which is at this point, feeds into this piezometer. So what we're doing in effect is measuring the total system losses between inlet at I and outlet at O. Now the losses in this system will of course be due to all the K factors, which will be all the fittings, and all the friction losses in that pipe. But the friction losses are minor, but based on such a short length of pipe. So predominantly we are concentrating on the K factors in summation, in other words the total. So with this practical, we obviously need a variety of data points so that we can draw some graph to determine the relationship, whether it's linear, quadratic and the like. So what we do, as always, is adjust different flow rates with the pump valve, and for each of these flow rates, based on Darcy-Weisbach equation, we should see differences in losses. And the practical suggests the different flow rates to be determined by a difference of 80, 160, 240 and 400 across the mitre. At the moment we've got approximately 65 or so, but that once again is not critical because it is just to determine a variety of data points. So in this case we would measure the difference between the inlet and the outlet and take away that value from this value, and that will be the head loss through the whole system. We will then adjust the flow rate to a higher flow rate, and notice quite interestingly that the differences increase as Darcy-Weisbach equation illustrates. The head losses are proportional to the velocity squared. We have a greater flow rate, therefore greater velocity, so we expect a bigger difference between the inlet and the outlet. We'll then adjust it to a third value, and at the third value also determine the difference between I and O, and so forth until we have enough data points to determine the pattern or the shape of the graph, or the relationship for that matter. The next part of the experiment is, or test 2, is to adjust the valve fitting. Now the valve fitting resides within our system, so it's one of the Ks that we had already encountered. Now if this is a gate valve, which I believe it is, the K factor for a gate valve fully open is about 0.2. So the practical suggests that we repeat for 5 readings with a difference of 80, 160, 240, etc. with the gate valve 3/4 closed. Now, or 3 full turns I should say. So with 3 full turns we should see some, obviously with throttling the system, we should see some changes in the levels. We're managing to see some changes, and then we repeat it for different flow rates, and for each of those flow rates measure the difference between I and O and determine the new graph. So we do it for gate valve open and gate valve semi-closed, and we know that for a 3/4 closed gate valve the K factors increase to 5, so there will be a dramatic change in in the cave based on the closure.